Good day, I'm Maile Matsiba. Welcome back to our channel. Today we're starting with class test 3 of our CIR 123, which is the second chemical engineering module at the University of Pretoria. We're looking at part 1 of the 2011 class test 3. So it says, the problem statement says, to produce synthetic gas, which is CO and H2 in the mole ratio of 1:2 in a laboratory, methanol gas is decomposed over a catalyst as indicated in the flow diagram. And also please note the chemical reaction equation. And then it goes further to say the fresh feed methanol gas contains 2% hexane, which is C6H14 as an impurity. And fortunately, the hexane does not decompose and it does not affect the catalyst if the concentration in the mixed gas charged to the reactor, which is stream A, does not exceed 14.6%. The methanol conversion in the reactor is only 25%. The gas mixture leaving the reactor is cooled to condense the methanol and hexane, producing pure CO and H2. Yeah, producing pure CO and H2 gases as products and allowing the CH3OH and C6H14 liquids to be recycled, right? And then it goes further to say part of this is evaporated before mixing with the fresh feed. Now another statement says use a basis of 100 kilomole per hour mixed gas feed. This is actually the mixed gas feed. Use the 100 kilomole per hour mixed gas feed to the reactor, which is stream A, to calculate the following. Now, this class test, or this part of the class test, actually has around 4 or 5 questions. So in this particular video, we're going to be looking at only the first question. So this is actually what the question says. It says, calculate the composition of the recycle stream. So the question is asking us to know what is the composition of the recycle stream? What's in the recycle stream? Percentage-wise. So now, if we're going to be answering that question, the first thing is to actually choose a basis. And since we are told that we have been given 100 kilomole basis of stream A, we'll use that actually as a basis. So basis is 100 kilomole stream A, right? So now, if we agree that if we choose 100 kilomole of the stream here, then that means that our C6H14 is going to be 14.6 kilomole, and also our CH3OH is going to be 85.4 kilomole. Yeah, 85.4. I needed to mention the 85.4. So we can just say, therefore, C6H14 is equals to 14.6 kilomole, and CH3OH is equals to 85.4 kilomole. Now, with that said, we know the composition of we know the molecular composition of stream A. Now, if we have that, we can now go to our step 1. Let me just write here step 1. Now, in our step 1, we're going to calculate the amount of CO and H2 that has been formed per 100 kilomole of stream A according to this reaction. So we're going to be calculating how much of CO and H2 is going to be formed. Remember, this is a decomposition reactor, so CH3OH is going to be decomposed and form CO and H2, right? But remember, we are also given information that the methanol conversion in the reactor here, which is the decomposition reactor, it's actually only 25%. So our question, our step 1 is we want to calculate how much of CO and how much of H2 has been produced in the decomposition reactor. That is our step 1. And let me just write it down. Calculate the amounts of CO and H2 formed per 100 kilomole per hour of stream A. So that is actually our step one. We're going to calculate how much of CO and H2 has been formed out of this decomposition reactor. So now with that said, we can actually, the first thing, the easier way to calculate this, especially because we have been told that the conversion in the reactor is actually not complete, it's 25%. So the best way is to actually calculate the theoretically possible HCO and H2 first, and then we're going to use the conversion factor to be able, or the conversion percentage, to be able to calculate the actual CO and H2 that is produced. So with that said, we can just say the ratio of CH3OH and CO is 1:1. That is according to this equation here. So it's 1:1. Therefore, CO theoretically possible is equals to 85.4 kilomole of CH3OH multiplied by 1 kilomole CO per 1 kilomole CH3OH. So basically what I'm doing is that I know that from this reaction equation here, we have been told that we already, based on the 100 kilomole basis of stream A, we know that CH3OH is actually 85.4 kilomole. And because of this reaction, if we have this, if it reacts all of it, we're going to actually have 85.4 kilomole of CO. That is actually the theoretically possible CO that can be produced. And that is actually what I try to calculate here. So if you use your calculator, it's going to give you 85.4 kilomole CO, because this will fall off. So which means the theoretically possible CO is actually 85.4 kilomole. However, let me just write here that but the conversion in the reactor is only 25%, right? Which means that the conversion in the reactor is actually 25%, which means 25% of CH3OH did react to form CO, right? And now, if this is the case, then we can just say, therefore, CO produced, so that is the actual CO that is being produced. CO produced is equals to 85.4 kilomole, which is the actual theoretically possible, multiplied by 25%, which is 0.25. And if you use your calculator, it gives you 21.35 kilomole CO. So now we know that in our stream B, we actually have 21.35 kilomole of CO, among other gases, right? Now we go, remember we are calculating not just CO, but also H2. So now moving further, we're going to calculate, now that we find how much of CO has been produced, we can actually use the CO to actually find how much of H2 was produced. So we can just say the ratio of the ratio of CO and H2 is 1:2, right? 1 CO is to 2 H2. Therefore, H2 produced is equals to 21.35 kilomole. We can just say 21.35 kilomole CO, right? Multiplied by 2 kilomole H2 per 1 kilomole CO. This can be some longer route, but it's very much easier. It makes it easy for somebody to follow. So that's why I prefer that. But some don't even need to write the kilomole H2, they just write the numbers. It's fine as long as you understand that. So now, if you use your calculator there, it gives you 42.7 kilomole H2. Now, going back to the equation, now we know that out of this process, the decomposition reactor, there's actually 21.35 kilomole CO produced, right? Let me just write per hour, per hour, it's necessary, especially because our basis is actually 100 kilomole per hour. Yeah, let me just fix that. It's 100 kilomole per hour, right? So, which means that we actually have, in the decomposition reactor, we know that 21.35 kilomole per hour CO has been produced, and also, 21.35 kilomole per hour CO has been produced, and also 42.7 kilomole per hour H2 has been produced. So with that said, this brings us to this actually concludes our step 1, and it takes us to our step 2. Let me just write step 2 here. Step 2. Now in step 2, we're going to calculate the composition of stream B. Calculate the composition of stream B. This is stream B right here. So after the reaction, after the 100 kilomole and part of it decomposed here, according to the 25% conversion, then we need to know how much is actually, what is the composition of stream B. And that is actually our step 2. And with that said, already we know that CO, we just calculated, we know that in stream B, CO is actually 21.35 kilomole, right, per hour. And we already also know that H2 is equals to 42.7 kilomole per hour, right? And we also know that C6H14 is equals to 14.6 kilomole per hour. Let me just briefly explain the C6H14. C6H14 is not interfered with. According to the information that we are told that it's actually an impurity, but if it's actually not more than 14.6% of stream A, it doesn't get interfered with. So basically it didn't react and it's still there. So what we know that only CH3O is the one that has been decomposed. So in stream B, all of the C6H14 that came into the decomposition reactor also came out of the decomposition reactor, not interfered with. And hence, that's why I'm saying that C6H14 is actually 14.6 kilomole per hour, right? And now, CH3OH is equals to, CH3OH is actually equals to 85.4 kilomole per hour. That is actually the amount of the kilomole that came into the reactor minus 20, because remember we are told that 25% of this did react. So it's minus 85.4 kilomole per hour, right? Multiplied by 0.25. It is the original, the whole CH3O3 minus the CH3O3 that has reacted, right? Or that has decomposed. And with that said, if you use your calculator, it gives you 64.05 kilomole per hour. So now we know very well that in stream B here, we know how much of we know that we have CO 21.35, H2 42.7, C6H14 14.6, and CH3OH is 85.4 kilomole per hour. Rather 64.05 kilomole per hour. That is actually our stream B here. And this concludes our step 2. Now it takes us to our step 3. Let me just write here the step 3. Right? Now in step 3, we're going to calculate the composition of streams C, P, and R. So let me say, calculate the compositions of stream C, P, and R. Let me just mention here that it's percentage. This time, in step 3, we're going to focus on percentage composition. Let me just bring... So this is actually our C, P, and R, right? So what we need now is to actually calculate our C and our P and our R, the actual composition of what's in there. So now, for us to do that, we're going to start with the composition of stream C. Let me just write here that the composition of stream C, right? In stream C, if you can check here, we are told here that it's actually a separator, and according to the information that we are given, in the separator, like stream B has been cooled. Let me just read it to you here. In stream, the hexane producing, the gas mixture leaving the reactor is cooled to condense the methanol and the hexane, which means 4 gases come in here as gases, right? But when they come in here, all of the hexane, all of the C6H4 and the CH3 that did not react get to be condensed, and only 2 gases are left now. It's actually CO and H2. That's why they are saying that the liquid produce, they call it pure. Yeah, it says to condense the methanol and the hexane, producing pure CO and H2, which means in here, after the separation, there are only 2 gases. It's CO and H2. And now the C6H14 and the CH3O4 has been condensed to be liquids, and that's how they become separated. And C here that contains only the liquid, which is what? C6H14 and CH3O4, and D here contains the gases, which is the CO and the H2 that has been formed. And we did calculate that it's actually 21.35 of CO and 42.7 of H2, right? So now our focus now is to calculate the composition of C. So we know that the composition of C is actually B without CO and H2, right? So that is actually what I needed to explain. So in C, we can just say that C6H14 is equals to 14.6 kilomole, right? And CH3OH is equals to 64.05 kilomole, right? So now this is actually the actual kilomole inside C. Now I want to calculate the percentage of each C6H14 and CH3O4OH in C. And with that said, I can just say percentage C6H14 is, okay, let me put per hour, sorry. C6H14 is equals to 14.6 kilomole per hour, right? That is actually the C6H14 all over the total, which is 14.6 kilomole per hour plus the CH3OH, and it's how much? It's 64.05 kilomole, right? Multiply by 100%, and if you use your calculator, it gives you 18.56%. So with that said, we know that in stream C, there's actually 18.56% of C6H14, right? And we go do the same for the CH3OH. So we say percentage CH3OH is equals to 64.05 kilomole per hour all over 14.6 kilomole per hour plus 64.05 kilomole per hour multiplied by 100%. And if you use your calculator, it gives you 81.44%. So now we know that in stream C, there's actually 18.56% of C6H14 and 81.44% of CH3OH, right? Now, we are done with C. We have the composition of C. There's something important I want to highlight here, that C does divide. A portion of CH3OH and also a portion of C6H14 did become patched, and a part of it goes there. So we see that the amounts of the moles of both CH3OH and C6H14 does decrease because part of it is patched, right? However, it's important to understand that those certain amounts get to be patched, but the percentage composition does not change. You see, so in R, in R here, obviously, the kilomole of CH14 is not 14.6 because a part of it did become patched. But the percentage, so the kilomole has changed because part of it has been patched, but the percentage did not change. So the percentage of C6H14 here is equal to the percentage of C6H14 here and there. So which means that the percentage composition of C and R and P are the same. And that actually is actually one thing I wanted to emphasize. And with that said, we can then answer the question. Remember, the question was saying that calculate the percentage of the recycle stream, and the recycle stream is actually here. Calculate the composition of the recycle stream. So if we have the composition of this stream that comes from the separator, then we can get the percentage composition of this stream. And that's actually what I wanted to highlight or to emphasize. So I can just say, therefore, percentage composition of stream R, right? That is actually what we're focusing on. C6H14 is equals to 18.56%, right? And CH3OH is equals to 81.44%. With this, we have answered the whole question. So thank you for your time. I hope we meet again in our next video.